Many of the other speakers took all the great things I wanted to say, but that's okay. I think that what this is helping perhaps reinforce is that many of us are on the same page in the industry, regardless of which company we're in. And we understand the importance of this technology, and it really is going to be a game changer, not instantly, but you can already see from the hardware vendors to the operating system vendors and hypervisor vendors how we are preparing for this new technology revolution. Okay, I'll try that. Okay, so I'm going to talk about a product that we're not yet shipping, and I'm just an engineer, so don't ask me any of those kinds of questions. Okay, many people have already mentioned this as far as local storage latency. Gosh, that really does seem to be a problem. Oh, okay, that works. That's not good. Feedback. Okay, so this is a great chart I sort of borrowed and then redid that was originally at a SNIA Flash Memory Summit. And it's really a great slide. What it talks about is you can have persistence, but latency is a pretty hard thing to attack, but we're getting better. So going from a hard disk with maybe a latency of 10 million nanoseconds, or 10 microseconds perhaps, all the way up to now NVM Express, which is somewhere in the neighborhood of 10 microseconds, or you could say 10,000 nanoseconds. Meanwhile, over here, there we go. Meanwhile, over here, we have DRAM with latency of 50 to 100 nanoseconds, but it's not persistent. Wouldn't it be great if we could take our chocolate and our peanut butter and have it together? And this is the point of persistent memory. So this is basically data that the processor can access like it were effectively DRAM. There are certain caveats. And with reduced latency at a byte granular level. So for this conference, we're calling it PM for persistent memory. You may also see it referred to as PMEM or other kinds of things like that. And the reason I'm standing up here on stage is because not only is the hardware technology now with us and shipping in much more volume, and a little later from the Death Star guys, it will be even super interesting. Now, sorry Andy, now we will actually be having a product coming out at some point, really soon before I die, that will bring the agility benefits of this to the data center that is virtualized. So many of our customers, and unfortunately these slides might be slightly higher level than this audience is used to. It was sort of a hit or miss. I apologize. Many of the customers we talk to are really confused by the terms NVM and NVRAM and NVM Express. So we attempted a simple diagram here. I'll just go over it briefly. I'm sure, again, for you, this is all background that you already have. Okay, this is going to be death of me yet. So here's sort of this non-volatile memory term that we're all familiar with. And in sort of a, if I ignore PMR for a moment, we have sort of a block access model that leads us to NVM Express and NVDIMF. And we have sort of a random access model, which you could say NVRAM is sort of one implementation of non-volatile memory. And NVRAM actually has multiple classes underneath it. And the next one, from our point of view, we're saying this is persistent memory, or PMEM, which is a type of NVRAM that is directly mapped and addressable by CPU load and store instructions. And NVDIMN, NVDIMP, and possible other technologies will sort of fit under as implementations of PM or PMEM. So, as you already know, what is PMEM or PM? Is it's byte-addressable persistent memory that has storage with the characteristics of DRAM latency and bandwidth, DRAM granularity and access. It's sort of a DRAM model for app software, modulo interesting cache flushes and other kinds of instructions. And it at least sort of fits into that standard OS paradigm of I know how to map pages and create virtual memory and nested translations in order to map this directly into an application. So a future version of VMware vSphere will enable persistent memory by supporting a virtualized NVDIMM device. Okay, again, for this audience, very basic. You're already past this, but I have found this helpful for some folks who are perhaps less familiar with this. If you were to look at the way we do block storage today in a traditional server, you are basically fetching some larger granule of memory. It could be 4K, it could be 8K, it might be 512 bytes. And our application here wants to change the value of 1 bit or 1 byte. And right now it's in red. And so that data has to come up into the processor package. It has to go into DRAM. And then the application program has to fetch the appropriate cache line of that data, make the change to the byte data in DRAM, and then initiate an I/O again to write it back out to the more persistent block storage medium. Now, yes, storage operations optimizations can remove a lot of this, and I haven't really shown the data cache in here because that would confuse things. But on average, this could be a read, modify, write duration of hundreds of microseconds. Yes, we can get clever, but just saying that's one way of looking at it. Whereas a byte-addressable persistent memory model says, after you've set up things, done your mmap and worked with the great APIs that Linux and Microsoft Windows provides, you can actually directly access with loads and stores. And so this really becomes updating the red to the yellow, simply becomes a cache line read and a cache line write. And again, a few additional operations to ensure durability or commitment to persistent storage. Other folks will talk about the persistent memory benefits, but none of this really makes a lot of sense without the applications on board. And I'm really excited, for example, that we have Microsoft SQL 2016 that can take advantage of this, and we have other applications that we'll talk about later today. Without the applications, it's not of interest to our customers. Okay, so we've spent a lot of time so far at this summit talking about how a bare metal operating system can take advantage of persistent memory. And so here's a trivial, simple model here. We have an application. It goes through, this is a legacy OS, an OS that has not been modified in a while. And it still wants to take advantage of persistent memory. And it can by using a special driver that can be installed into the operating system that will expose this as sort of a block mode device using mmap and the kinds of interfaces that have already been discussed. Okay, that's great. What can we do for virtualization? Well, we can actually use the persistent memory as a block storage device with a special driver in the VM. So we could do the same thing that's happening in native, but also with the future version of vSphere, we can actually provide an uplift with no special driver required in the virtual machine. What we can do is we can actually take this virtual SCSI disk that is in the virtual machine, and we can, behind the scenes, map it to persistent memory when the file sync operations are occurring through our normal vSCSI emulation. So that's a thing we can do that means your virtual machine that has not been modified can take advantage of this. There's also the model for us, why this is important is we do not want to change to the guest OS or application stack for these old dusty deck virtual machines, which our customers don't want to touch. Well, up until a couple days ago, nobody wanted to touch any of the operating systems. So anyway, so this is sort of the legacy view of how virtualization can be used for this. And a speaker from Microsoft also described how Hyper-V, again, can sort of virtualize this for virtual machines. A future version of VMware also will support a better interface for new operating systems and applications. So, gotta love this. Okay, so for native and virtualized, because we are now using a software stack that understands persistent memory, we can use a direct load store model with little OS overhead once this is set up, and all the benefits that we can provide in a hypervisor can be made available with this model. So here I've shown actually two different virtual machines that could be running different operating systems, and we've partitioned the real persistent memory into regions that are appropriate to map into each of these virtual machines. And we can also still do the vSCSI emulation as well. So that's one of the important things, is we can make better use of persistent memory than you might be able to in just a single operating system environment. This also allows the possibility of live virtual machine migration. It allows for checkpointing, and it still provides that boost for legacy workloads, legacy virtual machines. And there are other things that we can do with it. So we think this is going to be an important game changer, assuming that you have the applications that know how to take advantage of it. They can run side by side with applications that don't know anything about it, yet they can still benefit from persistent memory as well. Another thing I'll just point out is that of course, we do not need necessarily to map all of the persistent memory into a virtual machine that might be using it. It can be somewhat on demand. You could potentially even consider the persistent memory in a server as really just a local storage place, a local cache for where the full persistent memory image may live somewhere out in the network. There are lots of things you can do once you can sort of put an abstraction between you and the hardware. Now, there are a number of persistent memory technologies out there. I'm going to talk about three because I just want to help give you an idea of where we are. One of the key things about persistent memory technology, if you haven't figured it out, is how do you actually ensure that the data is truly committed, architecturally serialized, in the possibility of a power fail and also system shutdown. And vendors have spent a lot of time trying to be clever on this, and so it influences how their architectures work. So the first one is NVDIMM-N. So this is effectively where you have a memory-mapped DDR4 DRAM backed to NAND flash on shutdown or power fail. And there are basically examples of this right now from Dell, HPE, and we will be supporting that when we come out with our product. And each of these have some sort of solution, be it a lithium-ion battery, a UPS or something, to provide enough power to ensure that any writes that are sitting in this DRAM, and in fact all of the image usually is sitting in the DRAM, there's enough time and enough current so this controller can write this DRAM into the actual persistent media. Now, you may hear that the endurance of NAND flash, is, it could be 10 to the third to 10 to the fifth program erase cycles. But remember, this is only going to get written to every time the system shuts down or has a power fail. So it's a much longer time period. And meanwhile, it's using DRAM. Okay, the next one is something that I'm most familiar with, what HPE has done with their scalable persistent memory. This is DRAM that is on power fail or shutdown, written to really fast external NVMe Express devices. You need, obviously, a little longer power budget to be able to do that, but they have a successful product they call HPE Scalable Persistent Memory, which does. The nice thing about this is, unlike NVDIMM-N, which maybe is 8 or 32 gigabyte DIMMs, you can use standard RDIMMs, and that should have said RDIMM for NVDIMM-N as well. You can use standard RDIMMs all the way up to whatever the technology supports. So if you have 2 terabytes of 128 gigabyte RDIMM, you could partition 1 terabyte of it to be persistent using this technology. And both of these give you both NVDIMN and HPE scalable persistent memory, give you the access characteristics of DRAM. Lastly, there's a technology that Intel has been talking about, which is 3D crosspoint technology. And this is a case where the backup is a little different. This technology, you're not, in general, writing to some sort of large DRAM cache or anything. You are effectively writing your persistent data directly to the media. And it has some pretty cool characteristics as far as estimated capacity. The latency is estimated to be hundreds of nanoseconds. The endurance is a lot better than NAND. And it has a load store model just like the other two. And I do want to say that VMware will definitely be there with Intel when they launch this technology. And I think it can be a real game changer from the cost point of view for systems. But stay tuned, that hasn't happened yet. Okay, so here's an example of where we effectively have virtual machines, and they want to be able to use persistent memory in one form or another. And you could envision that the persistent memory that they desire to use, which is really part of the VMDK, the set of files that describe the state of a virtual machine, have been placed resident on whatever local storage is needed. And so you could manually move these virtual machines to a target server with persistent memory. Okay, that's nice. You could also, using our vCenter product, which is sort of a cluster-wide orchestrator for hosts running our hypervisor, you could also have vCenter and our distributed resource scheduler do this for you automatically. And it can make the decision where to place the virtual machine in order to sort of mate it with the data that it requires. Now, one of the other cool things about the abstraction, so Tom from Microsoft talked about various standards such as ACPI and UEFI, and there's SM bias as another requirement in there. Those are all important interfaces. We use that ourselves on a system. We also have to virtualize that properly, so when we run Linux or Windows in a virtual machine, they see the same kind of interface that they would see on raw hardware. So we have the advantage, because of the abstraction, is that we can take a virtual machine and run it on, say, Dell NVDIMN, move it over to HPE scalable persistent memory, and actually move it over even to Intel 3D Crosspoint without the virtual machine needing to know about which particular persistent memory technology it's running on. We think that's a pretty cool thing. And you can do that because of virtualization. Okay, so one other point, 5 minutes left. One other point is, so yes, live migration is very important, but there are times our customers tell us when they want to be able to not only migrate the virtual machines off a particular host for the persistent memory, but they also want to know that that data has been securely erased. Just like you can do with certain self-encrypting, self-erasing hard drives. So that can be supported by entering maintenance mode and vacating the virtual machines, and then effectively using other tools to make certain that that data is securely erased. And then, of course, you can migrate the VMs ad nauseum. Okay, so from a performance point of view, this is a really important slide. We did a measurement on an experimental persistent memory server with an experimental version of VMware and a not experimental version of Fedora 24. And we tried to, this is a quick and dirty estimate of comparing a virtual machine that's using our standard vSCSI emulation to a physical NVMe Express SSD. That's the light blue. We compared that with VMware using our vSCSI emulation to a persistent memory device. That's dark blue. And we compared that against a new operating system, in this case Linux, that is exposing, that knows what an NVDIM is, and we can map a virtual NVDIMM into it, but it's still using a block access mode. That is the ugly color of green. And then finally, a direct access where we're using DAX mode in a Linux environment. So for 4K, let me just pick one number that's interesting here. For a 4K running FIO, for 4 kilobyte random reads, light blue is don't do anything, do what you've already been doing. If we simply map the virtual SCSI emulation for the disk from an NVM Express SSD to persistent memory, we go from 1.2 gigabytes per second to 1.7, just by a simple change with no changes inside the guest OS. Simply, hypervisor is smart enough and the administrator indicated, please do that optimization. If we then run a block mode virtual NVDIMM access, we're about 1.9. And then if we actually allow DAX, then we're up to around 2.6. So for 4 kilobyte reads, random reads, that's not too bad. The really interesting thing is what happens here for 512 kilobyte random reads and writes, where now you can really see the benefit of directly using the virtual NVDIMM device in direct access mode. And even in the case of just our persistent, our emulation, our vSCSI emulation to persistent memory, you still see, well, it's more than, it's less than 2x, but it's still not bad going from 1.5 gigabytes per second to 2.4. The gentleman that spoke before lunch from Calypso, Dan, I can never forget that name now. He has much more details and a much better sense of humor and delivery than I do. Okay, so in conclusion, we think byte-addressable persistent memory is a fundamental change in storage and database architecture. You are now seeing multiple persistent memory technologies from a number of vendors. We can give some uplift to legacy operating systems and applications which can't be modified. The new operating systems and the applications using the SNIA model, and let me give, I know Andy's head is already swelling, but it was because of Andy Rudolph that I personally believe VMware really understood this programming model and how to embrace it, and his efforts, I think, which made such a significant difference in the industry for this application model. Because of his efforts, and maybe there were a few other people at Intel, we have a pretty workable programming model. And a future VMware vSphere will unlock persistent memory data, chain to a server, will unchain it, and bring the agility benefits of persistent memory. Thank you so much for your time.